welcome back to the channel. So today we'll be looking at May-June 2025 paper 44. So this paper just came out, just got released, and I find it really interesting that this particular session for May-June series 2025, Cambridge actually made 4 variants of paper. We have 4.1, 4.2, 4.3 and 4.4. Usually it's just 1, 2, 3, and now there's 4th variant also. So no idea why they did that, but anyways, the grade threshold for all the 4 papers aren't really far apart. They're just 2 or 3 numbers different, like one is 60, one is 64, 62. Yeah, it's just around there only. So they created the paper equally lah. But anyways, without further ado, let's look at question 6 from paper 44 May-June 2025. This is about magnetic field. Okay, let's get to it. A rectangular coil PQRS of wire is free to rotate about its axis XY as shown in figure 6.1. Okay. The coil has length QR of 5.4 cm. Let's start labeling 5.4 cm. Okay. Width PQ was 2.5. It has 190 turns of wire. This is very important for calculation especially. The plane of the coil is at angle theta. Is the angle to a uniform magnetic field of flux density 5.2 times 10 to the power of -3. The axis XY of the coil is normal to the field. Okay. The current in the coil is 1.2 ampere. Alright. First question, A Roman 1. Calculate the magnitude of the force on the side QR of the coil. Okay, so they want this side. Okay. So we know that we have a formula for force is F equals to BIL sine theta. Your magnetic flux density is 5.2 times 10 to the power of -3. Make sure you check your unit, okay? Sometimes they give you in milliliters lah. So check. 1.2 ampere. Your length, okay. This is the part you must be very, very careful. The length here is the length that the force is acting on. Okay. So based on this end view diagram, they said there is force on PS and force on QR. That means there is force here and there is force here. Right? Based on this diagram. Now, if you're wondering what is this end view means taken from this side. That is why your PQ looks slanted like that. Yeah. Okay. Anyways, coming back. So, the length here is referring to the length that your force is acting on. So, the length that your force is acting on here on the side QR is 5.4 cm. Not 2.5. Okay? And not 2.5 plus 5.4 cm, no. It is the length which the force is acting on. And it is 5.4 cm. So be aware of where your force is acting on and which side are they asking for. And this would be 5.4, and since it is in centimeter, we need to change it to meter, so times 10 to the power of -2. Then, are we done? No, we're actually not done. If you're wondering what is the angle, well, the angle is sine 90 degrees. Why? Because here they did say that the axis XY of the coil is normal to the field. So if this is 90, if I were to erase this, this would be, okay, that doesn't look like a 90. This would be, all this would be 90 degrees as well. So that is why it is sine. If you want to write, you can write it, sure. Sine 90 degrees. But this gives you 1. Sine 90 is 1. Now, are we done? No, we're still not done. You need to times by 190. Remember, we saw here 190 turns of wire. So you need to multiply 190 turns of the wire. Why? So there is 2 main reasons for this. One, your force is not acting just on one wire. It is acting on all 190 turns of the wire. That is one reason. The second reason is based on the definition of magnetic flux density. Magnetic flux density is defined as the force per unit current in a wire of unit length that is perpendicular to the field. That means, in other words, in simple words, flux density is for one wire only. That is the meaning of flux density. Magnetic flux, that is different. Magnetic flux is the product of flux density multiplied by the area. That is magnetic flux. Magnetic flux density and magnetic flux is not the same thing. Yeah, I repeat, magnetic flux density is for one wire, and in this case there's 190 turns of wire, so you need to times by 190 to know the total force. And magnetic flux is the product of this flux density multiplied by the area. For example, I have an area here. This is area, put A. Then you have flux density going in this particular area. And your magnetic flux would be, you take this flux density multiplied by your area. In other words, magnetic flux is the whole thing, is the total magnetic flux density acting in an area. Flux density is just acting for one single wire. That is flux density. So please know the difference between flux density and magnetic flux. And the definition of magnetic flux density and magnetic flux is also different. So they are not the same, yeah? Yeah. Flux density, magnetic flux density is for a single wire. Magnetic flux is the total density, total flux density acting in an area. That is why it's flux density times by area. Okay, now coming back. So don't forget to times 190 because two reasons. One, force is not acting only in one wire, it's acting on 190 turns of the wire. And this flux density is referring to only one wire. So you need to times 190 to know the total forces. Okay. So you do your calculation, you would get 0.064 Newton. And that would be your answer. There you go. So the part that you have to be very careful is this part. 190 and your length. Okay, other than that, you are good to go. Now let's move on to Roman 2. Use your answer in A Roman 1 to show that the torque on the coil is given by this. Okay, so we need to show this now. So first of all, let's go back to the base formula of torque. So torque, the formula is force times by the perpendicular distance. So these are the two forces that we know. So I think it's best if we look at this end view, right? Easier to see. So we have one force here, and this is basically going to cause the, what we call this particular, like if this is a frame, like the frame to turn, right? Okay. Now the torque formula we said was just now was force multiplied by the perpendicular distance. So the perpendicular distance here is this, right? Not this, It's not this. This is not perpendicular. You have an angle here, which is less than 90. This is your perpendicular distance. So how do we find that? Okay, let's see. We have some information definitely. PQ has a length of 2.5 cm. So if this whole thing is 2.5 cm, for you to find this length is, you find what is 2.5 divided by 2, because you need to find this line here. So this would be 1.25. Okay, let me erase the highlighter as well. This will be 1.25 as well. Alright, because the whole thing is 2.5. The easiest way for you to calculate this is to actually separate them into half. You can't calculate all together like that. It's a bit hard. Yeah, so using Pythagoras theorem, now you want to find this thing, right? Just going to label it as x. which is that 2. So let's do one by one. We find this x, then we multiply by 2. You're going to get the whole line. Okay. So Pythagoras theorem, I'll show you slowly. Cos theta is, we're going to use cos theta here because this is adjacent, right? Adjacent over hypotenuse, which is 1.25. Hence your x is 1.25 cos theta. And we want the whole line. That means it's 2x, hence it's 2 times 1.25 cos theta. So let's go back to the question here. So our force from our answer here is 0.064. So equals to 0.064 multiplied by 2 times 1.25 cos theta. And you would get 1.6. Oh, wait. Thank God I realized. 1.25 here is in centimeter. Change it to meter, yeah? Don't forget. Thank God I realized it. Times 10. Actually, if you calculate, you realize that you have not changed it. Cos theta. And you would actually get 1.6 times 10 to the power of negative 3 cos theta Newton meter. Shown. Okay. Alright. Now, let's move on to Roman 3. Using the expression in A Roman 2, sketch on the axis of figure 6.2 a graph to show the variation of the torque with the angle theta for values of theta between 0 and 360 degrees. Label the torque axis with an appropriate scale. Okay. First of all, let's look at our equation here. Our equation here is a cos theta equation. That means you're going to get a cos graph. So if you put cos 0 is 1. So if this becomes, let me use a different color. Okay, this green. If this becomes 1, that means your value is only 1.6 times 10 to the power of negative 3. Then when you sub in cos 90 in here, you're going to get 0 because cos 90 is 0. And so is cos 270. So this 2 is 0. Right, because if this is 0, the whole thing becomes 0. Right? Yeah. Cos 180 is negative 1. So if this is negative 1, this whole thing becomes negative 1.6 times 10 to the power of negative 3. Cos 360 is 1 also. So you're going to get the same value as cos 0. Okay, so let's plot our graph. I'm going to put this as 1. And this as negative 1. Okay. Let me put the line properly here. So like we said just now, cos 0 gives you 1. So your value would be 1.6 times 10 to the power of negative 3. So if this is 1, this would be my 1.6 times 10 to the power of negative 3. Then 90 is 0, okay. 180 would be negative value, right? So negative 1.6 times 10 to the power of negative 3. This is 1, this is 5, this will be the answer. Okay. Then 360 is the same as 0. Okay. Now, it is like a cosine graph, right? Yeah. So always double check with your function. If this is cos graph, you should get, if this is a cos equation, you should get a cos graph. So let's draw. I hope it turns out. Oh my god, it turns out better than I expected. Okay, yeah, this is a very nice graph. Okay, so yeah, there you go. Make sure you label. You can also label here if you want. Negative 1.6. Negative 1.6. Yeah. There you go. Make sure you curve here, okay? Because don't draw a sharp edge. Don't. Because cosine graph is never sharp at that point. Yeah. And you will get your 3 marks. There you go. Okay. Last one, B. The coil is now replaced by an identical coil wound around a ferrous core. Okay. Suggest with a reason how the torque on this coil compares with the torque on the original coil. So what is this ferrous core actually? So this ferrous core is actually something that can actually reduce eddy currents. Okay, you can reduce eddy currents, and when you reduce eddy current, you have reduce energy loss. Like when you reduce eddy current, you will reduce the heat energy loss. But that is not related to this. I'm just telling you. The one that's related to this is something called magnetic permeability. So this ferrous core has a very high magnetic permeability. So what is magnetic permeability? So we know you have a formula of F equals to PIL, right? This is something that you learn, right? There is another formula that is not officially introduced in the new syllabus, but I believe it was used in the older syllabus, which is B equals to this constant. I'll explain what the constant is later, just in a minute. Okay, this constant is called permeability of free space. This is for magnetic field. You have seen a similar one which looks like this, and this is called I hope I'm spelling it right. I think it's double M, right? I believe it's double M. Wait, let me check. Yeah, no, it's double T. Sorry. You need to get our spellings right. Permittivity of free space. This is used for electricity or electric field, and it's called permittivity of free space. For magnetic field, it's called permeability of free space. And this is given in your formula sheet. If you are not sure where is that, it's actually here. I've highlighted here. This is permittivity of free space. And if you realize, permeability of free space is not given, because like I said, this formula is not really introduced in the newer syllabus, but old syllabus you have used it. And it's good to know, because sometimes it can come really handy, especially in cases like this question. So coming back, ferrous core has actually a very high magnetic permeability. So when this is very high, your magnetic flux density is also very high. So your magnetic flux density is also very high. You have a greater force. You have a greater force means you have a greater torque. Am I right? So you can write here, ferrous core increases the magnetic flux density, and therefore the amplitude of torque increases. Now, why did I use the word amplitude? Because in this graph, the torque is on your y-axis, basically on the amplitude axis. So when your magnetic flux increases, I say your torque will increase. Right? So as your torque increases, what happens here? Your amplitude would increase as well. So amplitude of torque increases. In other words, you can also mention that the torque on this coil, on the ferrous core, on the coil that is wound around a ferrous core, is greater compared to the torque on the original coil, because they ask you to compare it, so you can just say comparison like that. And you get your 2 marks. Total 10 marks. And that's about it. So a few parts that you need to be aware of. First thing is your length and your turns of coils. Also your angle. In this case, it's sine 90, so you're good to go lah. Yeah, so these are the things you should be aware. And the difference between flux density and magnetic flux. Magnetic flux density is just for one wire. Magnetic flux, you can just like a total flux density acting in an area. So there's actually a difference. Even the definition of both is different. Yeah. Then at this part, remember to take the 90 degrees distance. The distance that is perpendicular to the force, not the slanted one, okay? Yeah, that is one. Then the graph should be okay, because all you need to do for the graph is sub in the value inside. And make sure your calculator is in degrees. If it's in radian, then you won't get. Yeah, and check back your function. If it's cos function, you should get a cosine graph. And this one is something that it's not of course introduced in your syllabus, but it's of course good to know, because in this case it's very useful. But if in exam, if they ever want you to use this formula to do any calculation, they should give you, because it's not really in the newer syllabus. Yeah. So that's all for today's video. I hope you gain a better understanding on magnetic field and for this question as well. I'll see you in the next one. Take care of yourself and remember to stay hydrated. Bye bye.